Can you see my screen?
Yes, sir.
Yes, sir.
All right. All right. So hope everybody had a good exam. So I have not checked yet, but hopefully this weekend I'll be able to check. So if you have any question, or you might be interested in knowing the answer to the question, right? First question, right? Yeah, so I'll explain. I think I'll explain the first one before I go further in tangent spaces. All right. So still, what do you think? It will be manifold or not? So what was the question? So question was the set XYZ in, what was the name set, M or S? Doesn't matter, but R3 such that x cube plus y cube plus z cube, was it equal to 1?
Yes, sir.
Yeah. Okay, and x plus y plus z equal to 0, right? So question was whether S is a smooth manifold. Right? So how many have tried to show that is a smooth manifold? Yeah, who is confident that you have correct answer? Nobody? Well, the first thing, you must have tried is whether you can apply implicit function theorem, right? So what was the function? Right? F from where to where?
So from R3 to R.
R3 to R3 to
R2.
R2.
yeah, right. Yes, R2. To define, you have to define a function by f x y z to be x cube plus y cube plus z cube. You can take -1 if you need, or you may not. X plus y plus z, right? And S is nothing but f inverse 0, 0. Yeah. Right. Now you want to apply, well, implicit function theorem. Let us try to do that. So what is Jacobian of f? Let me write it, df. Since we are working in case of calculus just, so let us just write calculus notation at x, y, z. So what will be it? So if you consider u to be this one, v to be this function, right? This is del v, del u by del x, del u at x, y, z, del u by del y, del u by del z, and del v by del x, del v by del y, and del v by del z at the point x, y, z. At this one, at the point x, y, z. Now what is it? Very easy to calculate. I think everybody have calculated this much. So del u by del x, 3x square, del u by del y 3y square. Del u by del z 3z square. Right? And this is 1, 1. No, there is a problem. There might be, I mean, you need rank to be 2, right? Yeah. You need rank to be 2, but there might be a problem here. Rank might be less than 2 somewhere, some points, right? So what are the points where rank is 2? Rank is less than 2. So first look, let's find out what are the points of R3 where the rank of df xyz is less than 2, right? So what are those points? So those points are all such xyz such that 3x square, 3y square, 1, 1, this determinant is 0, 3y square, 3z square, 1, 1, this is 0, and 3x square, 3z square, 1, 1, this is 0, right? Yeah, is it fine? So what are these points? Have you calculated, anybody? Yeah, what are these points? Come on, Buster, you
All of
must
them
be.
should be equal or like sign plus or minus each other.
That is true. That is true. So what you get, that is y is equal to plus minus x. That comes from 1. And here you can, from second you get 1 plus minus y equal to plus minus z. And last one, z is equal to plus minus x. Right? So this 2 is good enough. Right? One equation is redundant. So taking this 2 is good enough. This is kind of redundant. Right? Yeah. Now, this part you might have missed, most of you. So, are these points lying in the set S? Any of this?
Sir, if all of them are plus minus each other, then x
Yeah.
plus y plus z can never be 0 unless all of them are 0.
That's good. So, we have x plus y plus z is equal to 0 on S. So, this would implies whatever plus minus sign you put, this must be y equal to put y equal to plus minus x, z equal to plus minus x. Right? So what do you get? X is 0. X is 0. Let me write it in this equation. Oh, I had space here. So this equation, since xyz in S, x plus y plus z is equal to 0, this implies x equal to 0, y equal to 0, z equal to 0. The only point that has only point on that on that, only point of S on that rank of df is less than 2 is 0, 0, 0. Well, only point in not of S on x plus y plus z equal to 0, right? But now 0, 0, 0 lies in S or not?
No, sir.
It doesn't lie, right? So 0, 0, 0, this origin is not in S because x cube plus y cube plus z cube is 0, which is strictly less than 1. Of course, not equal to 1 is good enough for us, right? So what does this imply? What does this imply?
So
What is
for
the
every neighborhood, you can apply implicit function theorem, and you can find
exactly
path.
exactly right? So therefore can apply implicit function theorem near every points in S, right? So what do you get? S is manifold, right? So this would imply, well, we have some work to do, but that is done in class. So S is a manifold. A smooth manifold. Dimension, what will be the dimension? 3 minus 2, 1, right? Yeah, any question here? Any question? No question? All right. So let's go into the tangent space, which we are discussing before this class. Let us check once what we have done already, right? This was it, right? So this was just explanation of y equal to mod x. But what we have done is we proved chain rule in case of manifolds, and there is nothing special in that. We just hold accordingly, right? So a notation, recall that the notation, this notation is the notation for the derivative for a smooth map from between a manifolds, right? And chain rule, if you have a manifold, a smooth map from M to N and a map from N to P, then the chain rule gives you the differential of the composition is the composition of the differential. All right, and proof is very simple. I mean, if to appreciate the proof, you need to calculate, do yourself. Things are very easy, but let's say after you finish this course, let's say 1 month, you give a break, and perhaps you will not be able to do it unless you've done these things by your own hand. All right. So similarly, if you look at identity map, just the identity map, the differential for the identity map would be corresponding identity in the tangent spaces. All right. And we had a corollary. So if a map from M to N, smooth map from M to N is a diffeomorphism, then the differential at P, this is an isomorphism of vector spaces. All right, for a diffeomorphism F from N to N, the differential gives you an isomorphism between the vector corresponding tangent spaces. All right. Okay. I don't think we have done anything here. Let's go back. So an exercise using previous argument, diffeomorphism corresponds to an isomorphism of tangent spaces. Show that if U and U is open in Rn and V is open in Rm, and F from U to V is a diffeomorphism, then M equal to N. Then show that M equal to N. Well, what you need to look at is look at the dimension of the tangent space of Rn, which you already know. So let me note that as remark. Remark is the following. The dimension of TPRN is N. So dimension, of course, this is dimension over R as a vector space is N. All right. Now use this one, this remark. So first, if you are not fully satisfied, I mean, is my video freezed or what? Can you listen to me?
Sir.
Okay. So if you are not comfortable with the dimension of TPRN is N, you do it on your own hand. So you know the basis, del by del xi, I varies from 1 to n. This gives you a basis. So prove that this is actually linearly independent set. And of course, it can't be more than that. So any other vector from tangent space you take, it will be linear combination of those vectors. All right. So the proof of this remark is an exercise. So if you have not done yet, this remark is an exercise. I've done it, or I've said at least in some class. And then, of course, this you needed that one to prove that the differential of linear map is linear, which was an exam question. All right, any question here? So use this remark, first prove the remark and then use that remark to prove that, that if U and V are two open subset, one is in Rn, one other is in Rn, and if they're diffeomorphic, then it has M has to be N. But you have seen actually more, right? You have seen that the algebraic topological argument, right? Yeah. So this is simple differential geometric argument, but it needs a diffeomorphism. A topological argument does not need actually a diffeomorphism. A homeomorphism is good enough. So using homology, one can prove that the such two open subset, if they are homeomorphic, then the dimension M has to be equal to A. All right, you have seen it. Of course, if you know that, you can use it. But if you don't know the proof, this is simpler. I mean, once you give more assumption to the map, which is a diffeomorphism, then you get simpler. All right, any question here? No question? All right. So next one, we look at the basis for the tangent space at a point of manifold, a smooth manifold, right? Now, what is the basis for manifold? For Rn, you know, right? Now we have to use the basis for the tangent space r del by del xi for r del by del ri I from 1 to n. In case of when you look at Rn, then you use something to get a basis, right? So this is very simple argument. Can you just guess an argument or just think of an argument? What maps should you use? Any idea? No idea? Come on, there's a standard map. So what is a standard map for manifold? Very standard. Right. Yeah, Jitendra is right. So you can speak now. Yeah, so this is chart map. One use chart map. So how can you use chart map? Right. It is most of the time when you want to do something over a manifold, you need to use chart map. All right. This is the beginning, the starting point of anything you do there in the manifold, which are not topological. Topological, you don't need charts. To do something with functions, you need charts. So whenever you do analysis on manifolds, the chart is the most important object in manifold. You can't go directly the whole of it. You need charts. All right. So we consider R1, R2, Rn as the standard coordinates in Rn. M, let M be a manifold of dimension n, and P is in M. U phi is a coordinate chart around P, right? So you have coordinate chart. So is phi a smooth map? Is this a smooth map? Is phi a smooth map? Anybody? Well, how do you check a smooth map? Do you remember how do you check a map smooth or not? Yeah, Arundhati, can you tell me? How do you check a map whether it is smooth or not?
A map if from into N will be smooth if uh, phi compose if compose phi inverse is smooth over Rn.
Right. In that case, it should go to Rn. In this case, also the map phi going from U to Rn. So if it is going to Rn, then you just compose with the chart of inverse, right? Inverse of the chart. So in this case, you have phi as one chart. So phi compose phi inverse is identity. So what about other charts? Psi, let's say. Phi is phi compose psi inverse smooth? Yeah, Praful, can you tell me?
Yes, sir, it is smooth because F is manifold. So
Right.
there will be
Defining property of the smooth manifold, right?
yes.
Yes. So this is a, and it is also a homeomorphism, right? So this is a
Yes, sir.
diffeomorphism. All right. You check the inverse is also smooth. So once you get this diffeomorphism, then what do you get? Right? So what do you get? We got phi from U to phi U is a diffeomorphism. Right? So phi star P from TP M to TP Rn is an isomorphism of vector spaces by the corollary we proved last time, right? Now what is that? So what is phi star P of del by del xi at P, right? So let me write as proposition. So phi star, so if u x1 x2 xn is a coordinate system about p name then and of course yeah fees as above. So coordinate system around about p, right? Then so corresponding to the chart u phi. Then phi star p, actually much more is true, phi star q del by del xi at p is equal to del by del ri at p of, so we can actually put q here for all q in. All right. So this is true not just for the point P, it's actually true for every point in its neighborhood. Well, let's try to prove. So proof. So we look at the left hand side, V star Q, del by del xi at Q acting on F, right? So where does F belong? F belong C infinity phi of Q Rn, right? So this phi star map from where to where? Let's go back again. So phi star map. So this is important. This is very important. So phi star map here to here. So now del by del xi is a vector in the tangent space. That you already know. All right. It's a derivation. Del by del xi is a derivation. That part we already know. So we want to look at the image under phi star q. So q is any other point. So p is in a particular point, and q is varying in that neighborhood. So when you fix a point, it's basically linear algebra. So q phi star q this one is a vector space isomorphism. So it takes this one. So claim is this takes to del by del ri, which is the basis element in TPRN. All right. So since this is a vector in TPRN here, so it will be a derivation, so it will be acting on the function on Rn, and that's what we did. Now this one is by definition del by del xi at q f compose phi, right? Now what is the definition of del by del xi? Xi is a coordinate in manifold. So what is the definition? Those things you need to remember. What is the definition? Xi is just a notation, right? In a manifold, you just imagining xi has some coordinate system, but you are calculating all the time in the coordinates of Rn, right? So what is del by del xi? Mugilraj? Mugilraj, are you there?
Yes, sir, sir. Can you hear?
Yeah. What is the definition of del by del xi?
Del by dou by dou Ri of
Yeah.
at phi of Q.
At
Phi inverse.
you?
Phi inverse f of phi.
Phi inverse applied where? Which side?
F of phi.
F
Sorry,
of,
it is a f of phi of phi inverse. Sorry.
this is at f of, this is at where, at p of p, right? And this is
Yeah,
f
yeah, phi of p. Yeah.
p compose p inverse. So whatever is there, uh, whatever is there, the function, we apply phi inverse on that, right? So what is it? Del f del by del ri at phi p acting on f, right? And this is true for all f in this. So for all f here. What does this imply? This implies p star q, comma, maybe a comma is good here. Del by del xi at q is equal to del by del ri at phi p. P, no, not p actually, it's just q. Yeah, q. Right. So this is coordinate in a neighborhood, so we can do these things, calculus in the whole neighborhood. That is very important. It's q. It's q at f. Right? Sorry, f is already done. This is true for all f. So this is the truth. So in particular, this is also true for p. So in particular, this is true at q equal to p also, right? So this is what we claimed. See, there is nothing in the proof. What you need to know is to know the proper definitions and write these things. There's nothing more than that. All right. Okay. So now we conclude about the basis of TPM. So what will be a basis of TPM? Can you tell me? If u x1 x2 xn is a chart or a coordinate system, or like coordinate system term better, coordinate system about p, then the tangent space TPQ TTTQM has basis del by del xi at q, del by del x1, del by del xn at q is true. Yeah, for all q in u. The tangent space has this basis. So you should note that these things are defined in a neighborhood, right? Once the coordinate system is defined, like in Rn, it is defined globally, but for manifold, it does not define globally. So where it gets defined, it's defined on a coordinate chart. So with for all point in u, you can define this charts. This del by del x1, del by del xn, and you restrict some point p, you get a basis. Get a basis for for the corresponding tangent space. All right. Now, can you tell me the proof? This proof is already done by previous exercise. Yeah, so this is exercise. So this proof is already done by previous one. Oh, I had some gap here. Anyway. So here, I mean, corresponding to this proposition, so once you have this proposition, Phi is a diffeomorphism, and then and you gets into a basis, so the pre-image is also going to have the basis, right? That's what you need to show. So this is an exercise, and this is very simple exercise. Everybody should do it. Yeah. And it follows from here. Follows from here. So del and del by del Ri, I varies from 1 to n, gives a basis from Tq or Tf, T phi q Rn. Now we have isomorphism, so you get that side also basis. All right. Any question here? All these you will find in Tu's book. You need to, of course, these things, I mean, even if you read, you might get confused. So worst thing is to do on your own, and it will not take much time. All right. Any question? So we have the basis. Now how does basis changes? Right? So now the question is, how does the basis changes as we change the chart, which is coordinate system? You might want to see, so we are talking about coordinate system, right? And how do you explain coordinate system to common people? So if you see few pages of Einstein's just theory of relativity, there is this small book he has written for general public. You see, it took quite a bit of care to talk about what is coordinate system. Well, you might get confused as well. So there, because now you know exactly what is coordinate system. So there in English, he tries to do here and there to explain to common people how one can think of a coordinate system. Yeah. So how does the basis will change if we change the coordinate system? So what does it mean? It means the following. Suppose you have this is M, at P you have two coordinate system. This is U, and this is P, and we have another coordinate system V psi, right? Here it is phi of U in Rn, and it is psi of V, which is also in Rn. Right? Now you have two coordinate system, have two bases of the tangent space at the same points or every point here, in particular the point P. Now, how does this basis changes? Yeah, this is a valid question, right? Does it make sense? Does the question make sense? Well, if you fix a point, you know how it makes how it changes, right? How does two basis changes? How does this? How can you explain the basis changing in a vector space? What will be the relation between two set of bases? Two bases in a vector
So the
space.
coordinates will be multiplied by an invertible map.
Right. Right. So invertible linear map. Right? Yeah, Urshit, do you mean linear map?
Yes, sir, matrix.
Yeah. Right. So what happens here? Well, if you fix the point, it is the same thing. What you need to know is what are the entries of the matrix, right? So suppose u x1 x2 xn and v y1 y2 yn are the coordinate systems and p lies in u intersection p. All right. Then del by del x1 at p dot dot del by del xn at p this set and del by del y1 at p del by del yn at p. This both of them form basis of TPM, right? And with this since TPM is a vector space, this one basis is multiplied by other one, right? So we know from the vector spaces and the linear transformation that one basis del by del xi can be written, or let's say del by del xj at p can be written as summation a j k at p del by del yk, right? K from 1 to n. So this we know, yeah? So this one is from the property of vector space, from the property of vector spaces. Right, so you have two bases, and then you have this relation. The question is, what is JK P? Right, this we want to know. Yeah. So what do you think it will be? Any guess?
We can act on yk to get ajk. Del yk del x.
That's great. That's great. So, but what you need to know that this is true for all p, right? This is true for all p. So yeah, absolutely fine. So we apply. So which function did you tell? Yk, right? Or yi, yj, right? Yeah, aj, k was dummy. So let's find what is aij. So summation a k j p del by del y k at p, and we apply on the function y I, let's see, right? K from 1 to n, and this is nothing but aij at p, right? So this implies del yi del by del xi at p xj at p, right? What was left hand side? So this was this, right? So you apply yi on it, and this we get as aj I at p. Make sense? And this is true for all p in u intersection v, right? So what we get is the following: is del by del x j at p is equal to summation del yi by del xj at p del by k from 1 to n del by del y k. So this is the change of basis, and we would note that this function will be a smooth function. So the point is, you can very smoothly over neighborhood. Linear algebra gives you the formula for at one point, but then taking it as in a neighborhood and finding that this should be a smooth function, that will give you that this change can be done smoothly. Does it make sense to you? We'll use that. So this is true. This is true for all p in u intersection v. And note that we might have seen this is a smooth map, right? This was the Jacobian part, right? This was a smooth map. Yeah? So one can change smoothly. So that is the special thing you're getting here. And that actually leads to differential geometry. The geometry. So the structure of linear algebra are actually started moving using calculus. So this is one example. The structure of a tangent space is that moves around the point. You get the expressing change of the expression, and it gives also smoothly. right? Smooth change. Yeah. Okay, so we'll take around let's say around 25 minutes break, and we'll meet around 11:30 and have half an hour of some other things. Okay. All right. So see you that time. So I will see you at 11:30.